This is an optimization problem, which is a big part of the class. It says find the maximum possible area. So when we're done, we want a maximum area answer of a rectangle with perimeter 180 meters. So if we can, we draw a picture. It's a geometric situation, so we draw this picture. A rectangle, have two variables, x and y. We identify the quantity to be optimized is the area, which is x times y for this rectangle. We must have another equation called the constraint equation in order to tie x to y. So we look for that in the problem, and it says it right here. The perimeter is 180 meters. So the perimeter is 2x plus 2y, and that's set equal to 180 meters. We clean that up, which you always want to do. Simplify it if you can. And you get x plus y equals 90. That ties x to y. So the larger x is, the y is diminished, and within the constraint of it having to add up to 90. Okay, so this is an important statement right here. You must use the constraint equation to get the quantity that's to be optimized to be a function of one variable, because this is one variable calculus, not two variable or more. That's another course. That's for Math 263. Alright, so come over to here. Area equals x times y, but solving for y equals 90 minus x. Substitute that in, the 90 minus x for y right there, and you get the area as a function of x. And I wrote the area as a function of x. So you start off without the function of x notation on the a for area, and then you put the function of x notation as soon as you have substituted in and gotten one variable. Now we're looking for a level point, or maybe an endpoint of some interval, but typically it's a level point. So we're looking for a local max or a min of this function. This time we're looking for a max, a local max. So we set the derivative equal to 0 to find a level point, instantaneous level, where the rate of change of the function is 0 momentarily. Solve that out, you find a derivative, solve it out, you get 45. We put the meters, that's very important. When you finally answer the x, put meters. But that, what are we looking for? Maximum possible area. So we put the 45 into the area equation, not into a prime. If you put it into a prime, you're going to get 0. Put it into the original function a, and you're going to get 2025 square meters, and that's going to be your answer. But just to verify that it is actually a maximum, we take the second derivative. It comes out -2, which is always negative. That means a is concave down always, so that that point at 45, 225 will actually be a local max. In this case, it's actually a global max. Then you graph it. You always graph the function of one variable to make sure you found the correct point. 45 is right here. 45, 20, 25. It all checks out that it's a local max, concave down, and there's your maximum area.